Start the session. I'm Jan Grue from Norway, and in this session we have 3 talks from 3 different continents. And the first is from the United States, and that is actually Stephen Ackley, professor at the University of Austin. And before that, he was for 30 years at the U.S. Army Cold Regions Research and Engineering Laboratory as branch chief. It's a long experience with ice. So, please, Stephen.
Thank you. Thank you very much, and thank you to the organizers, especially Bernard Squire and Danny Feltham, who I pleaded and begged to come here, even though they well know that I'm not very astute in mathematics. So they reluctantly agreed, but anyway, I want to talk a little bit today about a couple of projects actually that we have been involved with because of the importance of the processes that are shown in this, and there's some results from the Sea State project in the Northern Hemisphere in the Arctic Ocean and the Beaufort Sea that Haley Shen is also involved with. And our recent project in the Antarctic called PIPERS, which stands for Polynyas and Ice Production and its evolution in the Ross Sea. So I'm going to give you a little bit of background on why we went to the Ross Sea and wanted to study it, and then I'll try to talk about the specific results on turbulence and pancake ice formation in Terra Nova Bay, Polynya, specifically where we spend a lot of time, and relate it to some, they also show some measurements from the Arctic, and so I'll try to point out as we go along, there's a lot of analogs between what we saw in the Arctic and what we're seeing in Terra Nova Bay, Polynya. First of all, I'd like to acknowledge the results from Madison Smith and Alison Kohut and the entire Piper science team. I was the chief scientist on the Piper's cruise, which, as most of you know, the chief scientists don't really do anything. They just sort of watch other people do stuff. So I'd really like to acknowledge their great amount of work. One of the motivations for this is the contrast between the Arctic and the Antarctic in terms of the duration and extent of the ice that's been observed. This is from Sharon Stammerjohn's work, and in the red here, this is ice season duration, and we can see all around the Arctic, and especially in the Beaufort-Chukchi seas, we've seen a much shorter ice season duration, or a longer open water period in the summer, rather ubiquitously around the Arctic. In the Antarctic, we see quite different contrasts in there, where we've seen a lot of ice loss over the years in the Bellingshausen Amundsen area, but actually the Ross Sea area is one area, sea ice area in the world that has shown actually an increase in ice season duration and also in ice extent, mostly in this area out here. So that was one of the motivations, is why is the Ross Sea peculiar in the respect in its response and showing increases on this, and there's been quite a bit of work that's related to atmospheric and processes, but we felt that it was necessary to go down there and really examine where the ice is coming from and why it's persisting in certain areas. This is also reflected in the results from the observed versus the modeled trends from Will Hobbs. And the Ross Sea area, as shown in the red circles here, for both the summer and the spring seasons, March, April, May, I'm sorry, the fall season, has shown the anomaly from all of the CMIP models. It's not well modeled, in other words, by any model in particular. So that was another reason for taking a look at the sea ice. The other motivation is oceanographic. Much of the Antarctic bottom water originates on the ice shelves and major ice shelves around Antarctica, and the Ross, the continental shelf and the Ross Sea is one of those areas. And if we, as I mentioned in the last slide, we're seeing more ice in the Ross Sea. But if you take a look at the trend of water, this is north of Ross Island, down in the interior part of that. There's actually been a freshening that's occurred and on the long-term trend, and a warming that's occurred. So the idea is that if you're making more sea ice, why are we seeing both warming and freshening of the Antarctic oceanic waters? Because the sea ice is the major source of the brine and so forth that transitions these shelf waters. So there's sort of a paradox in this area that we see more sea ice, but we don't see a commensurate change in that. And our principal hypothesis in the Pipers project initially was that we were saying that it really depends on where the ice occurs, and as you can see from this graph, that this is the net ice ocean freshwater flux, that we're actually seeing, this is the trend in that, we're actually seeing more sea ice in that continental shelf area, as opposed to the area out here where there's a lot more melting going on, and that's contributing to the freshwater flux around there. So it begged the question again, if we are seeing both the trend in ice production in that area, and this is an estimate from satellite imagery, so we're not so sure of it, and we are making more ice up on the continental shelf, which would contribute to the bottom water formation. Again, we're have this paradox facing us. So our principal effort was to try to see where the ice production is taking place, up on the continental shelf or out here, and also to take a look at the oceanographic changes that were in that area. Now, the coastal polynyas are around Antarctica are areas of intense heat loss and ice formation. What happens is that the katabatic winds are coming off the continent, gravity drainage winds, and they're very strong and very intense, and they tend to occur behind ice tongues or ice shelves that are participating. In the south, it would be the Ross Ice Shelf, so that the wind is also always persistently blowing away from the coast. A lot up further along the coast in Terra Nova Bay, we have the Dragulski ice tongue that sticks out into the flow. So behind that, we see the katabatic winds that can come down and keep that ice clear without other ice filling in behind it. So we have a tremendous amount of heat loss on this that's taking place in a lot of ice formation, and the newly formed ice is advected away from that area. So the thought has been that the polynyas are major ice producers in that particular area. Well, you can make the ice, but then you've got to move it away too. So that was the other question. And so the polynya formation processes and what type of ice is formed in there, and how what the brine rejection is, because that would lead to cold, highly saline water coming out of this area, are major factors that we wanted to investigate as well, to see what the role of the polynyas is in making the ice in the Ross Sea, as opposed to the ice further out on the continental shelf, or even away from the continental shelf. So this just shows us, the satellite data has shown us these increases in sea ice extent and duration and concentration, but the big factor is we don't know the ice thickness, and thus how the volume has changed. We can only get the area of the sea ice, the ice concentration changes, so we don't really know too much about it. It's very difficult to get, pretty much impossible to directly get ice thickness from space, so we're only having to rely on those measurements, and so we wanted to go down there and actually make specific thickness measurements as well. And as I mentioned, the sea ice production has increased, where and why. And the tremendous lack of in situ data, and generally winter data around Antarctica, is a major loss. This is only about, as far as I know, the only second winter expedition into Antarctica and into the Polynyas areas. The first one was the Lakes Glacier Polynya that was done by the Australians probably almost 20 years ago now. So these are our overarching goals. We wanted to improve the estimates of sea ice production and water mass transformation in the Ross Sea, and provide these first-time measurements of local and large-scale controls using a multidisciplinary, multi-platform approach, which I'll summarize a little bit. And the measurements were conducted during the 65-day cruise on the Nathaniel B. Palmer, the U.S. research vessel icebreaker, between 10 April and 14 June, just this past spring. So I want to reiterate that basically our equipment has arrived back into Long Beach, California, like 2 days ago. So there's still a lot of work to be done on calibrating and so forth. So you know, these are just sort of some of the very preliminary investigations. And during that time, we also deployed autonomous buoy arrays. We ended up deploying 4 autonomous buoy arrays to provide space-time observations afterward. This is kind of the new element that's into the work down in Antarctica relative to what's been done previously. I was on Ice Station Waddell, which is a drifting ice station, and that's what we used to have to do, is to actually live on the ice for a while and then make measurements continuously over time until somebody came and rescued us, of course. But now we can do this with these autonomous buoys, and they provide a very good time series from our snapshots that we do on these cruises. We also are using data from 2 airborne surveys. The NSF in the U.S. has an LC-130 that's equipped with what they call the ice pod. It's just basically a unit that fits into the door of the C-130, and it has all sorts of remote sensing equipment. And basically we're using the airborne LiDAR and photography, digital photography, and possibly some infrared measurements that are acquired on this, because the LiDAR gives us measurements of the downward-looking LiDAR gives us the measurements of the surface elevation, and then by the measurements that we made on the cruise, we hope to relate that to the total ice thickness. This is also a very important problem in the future, because they'll be deploying a new ICESat satellite, which is a spaceborne LiDAR, and they also will only be getting the surface elevation measurements. So we have to, in order to get sea ice thickness, we have to convert that in some way, and it may depend on particular conditions, how much snow cover we got on the ice, what the snow density is, and just the resolution of the LiDAR. So we were able to have this as part of our program. Now they couldn't fly during the period when we were down there because it's too cold. So they have to go down this November, so we're beginning that retrospectively. Okay, this this is a schematic, and we use this both in the Arctic and the Antarctic, and I think it's actually very illustrative. In the Arctic, you can think of this area as the ice edge and the open water area behind it. In the Antarctic, this is the ice that's coming off of coastal Polynya, okay? And we basically use very similar suites of instrumentation. Wave buoys, these swift buoys, which I'll describe in more detail. They measure waves, but also measure upper ocean turbulence. We have the ice mass balance buoys, automatic weather station that were put out. We had some drones on board that we used to fly aerial photography, and we had complementary satellite imagery from TerraSar-X radar Sentinel-2, the IcePod aircraft. There's a mooring in Terra Nova Bay run by Lamont Doherty. Chris Appa has that running. So we have time series measurements there, and also an autonomous underwater vehicle, which we use to map the underside of the surface. And as well aboard the ship, we had CTD measurements and some ice measurements, which I won't go into detail here, but I have other information on that. So this just shows you the cruise. This is the ice edge when we entered the ice on April 14th. And then we traveled down on this western side of the Ross Sea into Terra Nova Bay, and that's shown by the inset. Some people ask me, well, where is the Ross Sea? Well, if you take a look on this inset map, it's New Zealand is up here in Australia, so it's in this particular area. So we spent quite a while in Terra Nova Bay, about 12 days, which is kind of long for going back and forth, and you can see the multiplicity of lines in that area. Then we traveled over to the Ross Ice Shelf Polynya, made some measurements there, not too long, just some CTD measurements, and then traveled back out, and the ice edge had moved out to this position by the 5th of June when we exited that area. So just describing some of the wave measurements were taken by Allison Cahoot's buoys. We put in 4 buoys on the inbound track, and then we worked in this particular area, and then 10 on the outbound track. And this is not really the scale. The buoys were concentrated in the area from about 200 nautical miles from the ice edge in, but there are 10 buoys out in that area. And the idea was to capture the full wave decay over the marginal ice zone. It turns out that in this particular area, actually, we have nearly year-round, we actually have a melting ice edge. We're seeing, so it actually is very reflective of what Allison and Mike Malin and others did before to put in buoys, and we're seeing actually the attenuation, the breakup in the attenuation of the ice edge by incoming waves. In other areas in Antarctica, the ice edge will be growing out all the time by adding ice onto it, so the wave-ice interaction is actually quite different. It's during the ice formation period where we make a lot of pancake ice. But this particular experiment, I think, is probably going to capture the decaying ice edge, or at least the motion of the ice too is always to this edge, so it's moving out to kind of a constant position and then melting at that point, but you're always making ice in the interior and pushing it out into that area. This just shows how the buoys were laid out. We laid them out next to the ship, tried to pick 20-meter diameter floes, and it was put about 4.5 meters in from the side, and it's a little floating box. These are some measurements that Allison made in the Arctic, in the Arctic marginal ice zone. And what you see is the open water area. We have this position, but then with time, as the ice edge moved out, you see the attenuation spectra, especially in the high frequencies, in the shorter wavelengths, and less so in the long wavelengths. And this was quite reflective of, this graph shows the previous result, which shows that the very long waves have a smaller attenuation coefficient, a smaller decrease in amplitude with distance than the short waves that have both in significant wave height and in frequency, as we're seeing here. So the bigger long period waves are able to penetrate deeper into the pack. Oops, I didn't want to go that far. Hopefully this will play. Played before. There we go. This is from the Arctic, and what I said about this is very interesting because in the Arctic in the fall, what we're seeing is a lot of pancake ice formation. Pancake floes are formed by the collision of frazil particles, which are formed in the open water areas in this under fairly intense heat loss and the cold air temperatures. And we saw some very high amplitude waves during that cruise. One of the things I wanted to point out is that the breaking waves are really reduced here. You'll see a little froth over in this area, but that's from the bow wave of the ship. So that's another factor that we've seen, is that the breaking waves are really attenuated by the ice formation. So you can see the oscillatory nature of the pancakes moving back and forth. You also see some rafting of them as they're overriding under the action of the wave field. Now, the turbulent dissipation is sort of an interesting problem, and what was found in a previous experiment was that turbulent dissipation was found that very small amounts of sea ice would reduce the turbulence. And apparently the effect is what I just mentioned here, is the wave breaking stops it, and decreases the turbulence tremendously, increases the dissipation. So these were measured with these swift buoys, which I'll try to describe a little bit. There's a down-looking video camera. We have some nice footage from that. But they measure waves, the wave height, period, direction, frequency spectra, and directional moments. There's a wind speed anemometer on it with direction. And then air, water, temperature at about 0.5 meters, salinity. And near surface temperature from up-looking, these are aqueduct sensors that can measure near surface temperature and down-looking velocity profiles. So changes to the surface turbulence by the ice. This is the ice condition and the open water condition, and you can see again this attenuation in the wave frequency, but also in the dissipation. Basically, you see this decrease in ice suppressing the turbulence in the upper layers of there, and possibly some increase in there, which I won't go into, but so I don't know too much about it, but I can probably wave my hands at it if somebody wants to talk in a off-the-record kind of point of view. But basically, we're seeing a decrease in the turbulent dissipation from that. And as I mentioned before, the primary effect seems to be from the suppression of wave breaking by very, very small amounts of ice, very low concentrations, or in this case, pancake formation. This is very interesting. Let me go back a little bit here just to talk about what's coming up. What we'll see next is the movie taken by the camera from the swift buoy down looking, and as it's undergoing it's drifting, so it's a Lagrangian motion, and it's just taking a look at the ice formation right around the buoy. And what you'll see is a yellow line with a float on it that'll appear off and on in this, and this is a time-lapse movie over about 24 hours. So basically, you see the buoy going by. So this is dawn on October 26th. We get mixed open water and grease ice. Grease ice is just that thin film, that sort of matte finish on that. And it gradually evolves from grease to thicker frazil ice, just loose crystals, but thicker. And then we're starting to see pancakes forming, little embryonic pancakes. And then thin pancakes as they're forming, and you can see them maturing, growing and maturing in that particular area. And eventually reaching fairly large size. You'll see some bright spots on this, and this is from reflection from salt crystals that are being extruded out on the surface in the cold air temperatures. And you can see the pancakes forming much larger. So you can see that the oscillatory motions are very random, and they lead to these circular forms. And then eventually that was the end of the 24-hour experiment. But you can make pretty thick ice in 24 hours by pancake ice formation. What we were discussing at lunch, one of the reasons why you might be concerned with pancake ice evolution is what we had looked at a long time ago in some of the modeling, was that we had to increase the ice production at the ice edge because basically what you have, if you have a big diurnal cycle at the ice edge, if you only make a small amount of ice in that by normal congelation growth, what happens is that because of the strong radiation balance, it melts in that area, so you delay the advance of it. If you make pancake ice, you're actually changing the albedo a little bit, and so that while you might not be growing ice during daylight hours in the Antarctic, you won't be losing what you already have, and then you start another nighttime cycle of growing the pancakes. It's one of the things we've observed in trips to the Antarctic. A pancake ice always seems to appear overnight. It always grows at night, but it doesn't grow so much during the day. So anyway, this is the turbulence mechanism during that same swift buoy deployment, and what we're seeing up here is the significant wave height as the ice formation begins, and this is the wind speed, which stayed fairly constant throughout the whole period. This is the temperature at half a meter depth in the water, so we start off fairly warm and actually cools down. And then we're seeing a decrease, and I think in the first frame on the previous one, we saw that mixed grease ice and open water. And probably what's happening is that we're making a little bit of ice in that surface layer, but then it itself is cooling down the water column, so you see this gradual decrease in that. So these are still shots from that video bracketing this particular period of time. So we saw the mixed grease ice and open water, the thicker grease ice, and gradually going up into these full pancake forms over that 24-hour period. And these are the dissipation profiles that happened early on, and you can see that this cluster here, that the dissipation has the turbulence has greatly decreased during that period. I think this is a remarkable finding. It's really indicative of what's happening underneath the ice cover, both in the growing situation, and the previous ones were in a melting situation that Jim Thompson and Seth Zippel had shown, that as soon as you have a small amount of ice in the water from various mechanisms, could be very, very big in reducing the turbulence. So now we'll talk a little bit about some of the Antarctic work. And this over here shows a shot of the Terra Nova Bay polynya. It's bounded by the coast of Antarctica and Terra Nova Bay, which is sort of in between these points, Cape Washington and the tip of the Dragulski ice tongue down here. For those of you more familiar with Antarctica, the McMurdo Station and Scott Base are down just south of here. And this shows a shot of the ship transiting into this polynya, and you can see in the satellite imagery, you can see these streaks of frazil ice that are forming in this particular area. I hopefully can show the movie on that as we're transiting through there. And so we wanted to answer the question is, how does frazil ice formation vary spatially in polynyas, and is it related to formation of circulations? A lot of people have speculated that these might be Langmuir cells that were forming these streaks. I'll preempt my answer by saying I don't think so, but and I'll try to illustrate that a little bit, and possibly we can start a lively discussion on how these frazil streaks actually form. This is some work from modeling of turbulent dissipation and formation that Matsumura and Oshima ran, and these are some of the results from the SWIFT measurements corresponding to freezing and melting. These are frazil freeze melt rates, and this is freezing and melting situations in that, and I guess the correlation is pretty good with that model. So one of the experiments we were on went up into the Terra Nova Bay on the 5th of May, and this is a TerraSar-X, a high-resolution radar satellite image of that. And you can see that not only do we saw the streaks in the other area, but you can see this kind of large plume of whiter ice that's formed out in this particular area, and perhaps another one out here. And I've got other pictures that show that more completely. And what we had surmised from this is that these plumes, by the measurements that we made on the ground, you can actually trigger these into a particular katabatic wind event. So it appears that we're making, just kind of preempt the sort of take-home message, not only do we make a lot of ice in here, but under the action of the winds, we can advect it quite large distances out there. So the Terra Nova Bay polynya could basically account for quite a bit of the ice production in this particular western side of the Ross Sea. This is from the ship's weather log, a screen that showed there, and when we were going down there on the 5th of May, this is the GMT date here, is the winds got up to about 70 knots, 35 meters per second or so. And they dropped off into 50 knot winds, and that's when we deployed the swift buoy, because we thought, well, we can rescue it. And then the winds suddenly increased up in this area, so rather than a 2-hour swift buoy deployment, we had about an 8-hour swift deployment. And since I had commanded Maddie to put the swift buoy in at this particular time, I was pretty much shaking in my boots, wondering if we were ever going to get this thing back. And then even when the winds dropped off, it dropped off into about 30 knot areas. So we started calling this a half katabatic. There had been one previous excursion for just a couple of days that Martin Jeffries' cruise had been on in 1997, and they had also observed ice formation in the Terra Nova Bay, but they were down in a much lower range of winds down in this particular area. And what they saw was that the open water area was only about 1 kilometer or 2 wide, and we were seeing like 30 kilometers area where the winds were there. And the most dramatic effect was the waves that we saw during this. We saw up to 2-meter waves very, very close to the coast. So even with very short fetch, but with these high velocity winds, we were seeing extreme waves. And this little movie just shows the transect down through there, which I'll start here, I think. And what we're seeing is these frazil streaks. See, these are individual shots from this. We're seeing these frazil streaks, and then some of them you can see breaking waves occurring in the open water areas here. And you see these streaks, and then some of them you can actually see a sort of a curtain that's hanging down, and that's frazil. And there's been a lot of discussion about frazil forming at depth in these areas, but I think it might be because of the wave orbital motion that's really bringing the frazil down in there and pulling it back up. So then as these streaks move along, they sort of self-organize, if you will. They kind of gather into these wider streaks as we keep going along. So we eventually end up with very, very wide streaks, as you can see in the background over here, and we'll be going over those in a little bit. And you still see the breaking waves in that area, and then a couple of shots where you can see the frazil that seems to be hanging down underneath these streaks. But once the streaks get close to a bigger brother, they sort of attach onto it. And now we're going into one of these bands, and you can see the small pancakes already developing in that particular area. The complete absence of the breaking waves, and now you can see the longer period waves moving through that. And as we go along, you'll see these pancakes start to grow a little bit bigger in that particular area with time. And then the waves, and I'll try to show this on another slide, the waves seem to get kind of monotonic and unidirectional, and what you might see is some lineation in these areas. I'll try to point it out when I see it. Yeah, you might start to see it. There's sort of lines that develop here rather than just the random spots in between there. And so these streaks get wider and wider, and commensurately the open water areas get narrower and narrower. And eventually what happens is that they all coalesce together, and we have a continuous band of pancake ice that's formed in this area. And then that seems to advect out as this plume. We're going back into one of the areas of open water here, which is already filling up with lighter streaks. The ship was not exactly on a straight line course at this particular time, because what we were trying to do was follow the buoy, so it may make some sweeps into another area and go back to the west, more into the open water, and then come back into the more concentrated ice. The buoy is moving pretty constantly downstream. So I just wanted to show that these open water areas are starting to close off now, and we eventually get to this, you know, that's the end of it, but eventually we get to just a fixed point later on. This is, we had both a visible and an infrared camera. These are roughly commensurate shots, so we still have a little trouble. We haven't done the exact alignment of these two because they're taken on, you know, different discs, so we have to make sure we get the timestamp correct on those two. But on the infrared, you can see the small pancakes in here, but in the infrared you can see what I was mentioning before about the colder centers of these individual pancakes that outline them. I'll try to discuss that a little more as we have later. This is just another shot showing the slightly bigger ones. And so it's really nice, I think, from these infrared photographs we'll be able to get a nice measurement of flow sizes of these pancake flows as well. And we've got examples from further along in the development of these so we can get distribution of diameters of these. This is some work that Peter Wadhams is doing in association with his crews. And they're using Cosmos SkyMed, another radar satellite, to take a look at the wave action. And so this is the area that the Cosmos strip covered. And as I mentioned before, this is the narrower strips down in the western area, you know, gradually widening out until we get into this area of continuous ice here. And then further out, we see the development of the solid ice cover. I was very intrigued when I saw the other day when I think Vernon showed one of the wave spectra from the Arctic, which shows this a very highly aligned spectra when the waves are kind of high, and it led to that kind of opening up. But then as the waves die off a little bit, it looks like you're getting a much more isotropic spectrum here. So I'll leave it to the wave people to speculate on what's happening there. Scattering came to mind, but what do I know? And again, this is just the shot showing that band of the continuous ice on this. So just to kind of finish off on showing some of the other images here. This is the Ross Ice Shelf, McMurdo Sound, Scott Base are over in this area here. This is the Dragulsky ice tongue that we're just taking a look at. And this is the plume coming off the Terra Nova Bay polynya. But this is the plume that's coming off the Ross Ice Shelf polynya. And what we found in going down through this is that the winds are lower, the pancakes are thinner, but it's over a much wider area. So there's a good question as if when you take a look at the volume of the ice cover, there might be, you know, might be some partitioning between the Ross Ice Shelf polynya over a much wider area, but thinner ice and thicker ice and more intense advection that's coming out of the Terra Nova Bay polynya. So we'll be investigating that possibility to try to partition the amount of ice cover that's attributable to these two polynyas. This just shows another close-up shot, and you see the same sort of behavior, the streaks gradually coalescing into a solid ice cover. Now this is a shot out in the marginal ice zone when we were coming out there, and we see streaks and bands out here, but this is in the melting ice age. So that's a little bit tough, I think, in terms of trying to distinguish, you know, from remote sensing imagery, what's actually taking place, because we are seeing similar band structures or these fingers that are taking place in both the decaying ice cover and the formation ice cover. Mike Dinneman has done a little bit of modeling on this area. This is the mean thermodynamic sea ice production in meters per year. And what he's finding is very high in the model. He's finding very high amounts in the Ross Sea Polynya, but not so much in the Terra Nova Bay Polynya. So there's a question that the Terra Nova Bay Polynya may not be adequately modeled right now, and I think it's because of the intensity of the ice formation. The heat fluxes that were measured on site were over 1,100 watts per square meter when that ice formation was taking place. So there's a lot of ice formation. Because of the wave action and the formation of the pancake ice, we've got a lot of open water around, so the growth rates are very high, and we can make a lot of ice in this particular area. And then if you have a sequence of these katabatic wind events, as we saw there, and we'll be able to map these a little better because the katabatic winds, there's a automatic weather station at Inexpressible Island up in Terra Nova Bay, named that by one of Scott's expeditions, who wintered over there, I think, and the conditions are so bad they were inexpressible. That's why they named it, and it's because of the high katabatic winds. So over the whole winter season, we'll be able to map the katabatic winds, and then try to take a look and see from radar imagery what we're getting out of that particular area. So here's some just sort of bottom lines. We have ice formation in the Ross Sea Polynyas dominated by wave-generated pancake ice formation. And I might add that this is really interesting because in the Ross Sea, what we're making is the pancake ice in the south and then advecting it north. If we go over to the Weddell Sea, as we've seen in previous expeditions, we're tacking on the pancake ice onto the existing ice edge. And that's what we saw up in the Arctic at this particular time. So quite different locations for the ice formation in the Ross Sea and in the New Arctic and in the Weddell Sea. But we are getting the same ice form, we're getting the same kind of high ice production over that time. As I mentioned, the Terra Nova Bay katabatic wind forcing at high velocities generates high amplitude waves, increases the fetch and forms an advect ice at high rates. As I mentioned previously, with the lower wind speeds, the actual open water area and area of pancake generation is only about 1 kilometer or 2 wide. Here we saw about 30 kilometers wide before we had an intact continuous pancake cover. Terra Nova Bay Polynyas maybe are currently estimated. And the ice production in the winter Ross Sea may be primarily over the continental shelf. I think that that's indeed true. And field validation of concurrent satellite image provides a great tool for estimating year-round ice production in these polynyas. One other point I'd like to make, which I wasn't able to do here, was that we still are faced with the paradox. If we are seeing high ice production in this area, why aren't we seeing the, and that there has been more ice that's forming, why aren't we seeing the water changes? Fortunately, we were able to have Bryce Luce from University of Rhode Island on board, and he was measuring the noble gases in the water column, which can allows you to partition the sea ice production from glacial meltwater, which has been attributed to a possible cause in this area. So with that, I'll end, and thank you very much.
There is time for a few short questions. I think you were first. Please.
Hi, Stephen. A great talk, thank you. You didn't mention it explicitly, but those streaks of frazil crystals at the surface, do you think it's a Langmuir circulation that's starting that?
I don't think they are. I think they just form little bands, and then there might be some self-organization. If you get a little bit of ice on here, you could get, you might get drift to the left of the wind, and maybe they form on the left side.
I mean, in particular, the Langmuir circulations would form parallel to the direction of the wind, right?
Yeah.
So what direction was the wind blowing when you saw these streaks?
It was always straight out, yeah.
So
It was pretty much straight out, but I'm saying the drift of the ice might be, pulling those small bands into that area.
So are the bands parallel to the wind?
They are parallel to the wind direction, as far as I know. We will have to look at that more closely.
It could be consistent with Langmuir circulation.
It could be consistent, except that they grow,
Yeah, well, that's something else.
Yeah.
There is a question there, yes.
Excellent talk. It was excellent talk. I really liked the information on the turbulence measurements. comment on the modelling results at the end. It may be that the katabatic winds aren't really represented in the atmospheric products that have been used to force that, because that may be something like
Yeah,
that.
I think that's probably generally true. I don't know too much about the models, but I don't know if they explicitly have a way of putting katabatic winds in.
I mean, they've probably got them very good,
Right.
well off our ice
Yeah.
shelf, but they probably haven't got the topography right in that
Yeah,
Terra Nova
that's
Bay.
definitely true in the filtry running.
Yeah.
We don't get the katabatic winds in the reanalysis.
Yeah.
Yeah.
So, but even something like amps, reanalysis, you won't
Yeah.
get it at all. But
Even
like
though the
amps-
Ross ice shelf wind is you know, it can be called katabatic, it's a much lower velocity, and it's because of the persistent southerlies in that area. So it's not really the same as these drainage winds that are coming off high. Yeah.
even in a high resolution type
Yeah.
product.
We're a little bit into the next time slot. We have 2 burning questions. So
Just a quick one. So can I just confirm? So, what did you see the breaking waves in your Arctic region, the Morphos here? In
We saw the breaking waves in the Arctic region in the open water. Yeah,
Oh,
but
no,
not
the-
in the not in the pancake ice.
Not in the pancake field. So not in the pancake field. There was no breaking waves in the
There's no breaking waves in the pancake field. Yeah.
please, one question. Yes, please.
Do you think the bands of ice in the melting at the edge
Yes.
are the same mechanism? They wouldn't be pancakes, so what do you think that's going on there?
Well, maybe it's you know, all ice is alike in its self-organization in the bands. You know, that would make, because it really wouldn't be a Langmuir circulation in that case. I wouldn't think. You know, so that maybe it has something to do with the ice processes in both cases. Just to defy the Langmuir circulation argument a little bit. But, yeah.
So I think we have to stop there because
Yep,
it's the
sure,
next
of course.
episode. So thank you once again.